So in the case of natural convection, the heat transfer rate is given by HA delta T, where H is the heat transfer coefficient, A is the surface area of the heat transfer surface, delta T is the temperature difference between the surface and the ambient. And the dimensional for this particular case, for the vertical cylinder, people have earlier done the work, and they found a relation of Nusselt number, which is Nusselt number is a function of Grashof and Prandtl number. Nusselt number is a ratio of conductive resistance to convective resistance, or in other words, is the heat transfer by convection to the heat transfer by conduction, and it is given by HL by K. Prandtl number is a ratio of momentum diffusivity to the thermal diffusivity, which is equal to nu by alpha. Prandtl number and Grashof number is which appears in the case of natural convection study. So the Grashof number, since this is a natural convection study, the Grashof number is here, and it is calculated by G beta delta T LQ by nu square. G is the acceleration due to gravity, beta is the thermal expansion coefficient, delta T is the temperature difference, L is the length of the tube, and mu is the kinematic viscosity of the fluid. In this case, the air is a fluid. So the people have given the researchers have given C is equal to 0.59 and M is equal to 0.25, and with this help, Nusselt number is equal to HL by K, putting here and putting the constant value and substituting the formula, we get HL by K is equal to this much. This is equation number 1, and with with the help of this equation, we will find the H theoretical. This H will be a theoretical H, and this theoretical H will be tabulated in this fashion. In this is serial number. Q is the heat input, V into I, and H1, H2, H7, because H1, H2, H3, H4, H5, H6, H7, these are the theoretical heat transfer coefficient which will be found out by using this equation. Okay. After that, we will find out the average heat transfer coefficient in case of theoretical heat transfer coefficient, theoretical average heat transfer coefficient. So this is all about the theoretical result table. We will you have to plot the H with you have to plot a graph between H and position X, and the graph will come like this. So here there are 3 sets of equation, 1, 2, 3. So you will produce 3 set of graphs corresponding to these 3 readings in case of theoretical heat transfer coefficient. Okay. Next, we have to find out the experimental heat transfer coefficient too. So the heat transfer coefficient H is equal to Q by A delta T. Q is V into I. Delta T area, A is the heat transfer surface area, which is pi dl. D is the dia of the tube is 0.045, and L is the length of the tube is 0.45 meter. So putting these values here in this equation by using T average is the average of the T1 to T7. The T ambient is calculated with the help of this thermocouple. So by using this formula, we have H, which would be experimental one. This is the H experimental. So at each point, we have corresponding heat transfer coefficient, which will found out experimentally. So there is a need of separate table, which will in which experimentally obtained heat transfer coefficients at position 1, 2, 3, 4, 5, 6, 7 should be tabulated. Okay. Here 3 sets of experiments have been done at 3 heat input. So you have 3 sets of heat transfer coefficient at 7 different positions. Accordingly, you have to make it average H1 plus H up to H7 divided by 7. The H average will come here. In the same fashion as you will do in the theoretical case, there's another graph will come like this, H by X. For 3 sets of data, we have 3 sets of graph also in the case of experimental one. So in total, you should produce 6 graph, three each for experimental and theoretical one, and this result table. I think that would be, I think, it'll be easy for you. Okay, thank you.